All right, everybody. Today we're going to start some of my favorite lectures of the whole course. We're actually going to, with any luck today, we'll do both my favorite lecture in the whole course and my least favorite lecture in the whole course. So we're going to get the fun stuff over with first. Don't hate to say it that way, but we're going to talk about the origins of life. We're going to talk about what's called abiogenesis, how we could get from non-life, how we can get from basic chemicals all the way to complex organic life. This is the same sort of path organisms took here. It's the path that they may take on other planets. We don't know. We're going to talk a little about maybe potential extraterrestrial origins of life, things like that. I will tell you, this lecture is based on the most current, as of today, the most current literature out there. Does it mean that it is the absolute way that life began? No. This is our proposed hypothesis. This is where all the evidence is saying right now. Does that mean in a few years the whole thing won't change? No, it may change in a few years as we get new information, because that's the way science works. You get new information, you revise your viewpoint. And we're going to talk today about different theories and how one theory gave us some ideas, but then it was disproven, which then gave rise to a better If you're going to know anything, know this particular image right here, because it gives you the 4 distinct stages you need to get from non-life to living organisms. You will have an entire essay devoted to these 4 topics. Step 1, you got to get nucleotides and amino acids. You got to get the building blocks, the monomers. Step 2, those nucleotides and amino acids become polymerized. That is, they connect to each other. They're going to become proteins. They're going to become nucleic acids. Step 3, the polymers get enclosed inside of a membrane. So they get surrounded by, it might be a coacervate, it might be a liposome or cell membrane, but they get enclosed by like phospholipids. And then step 4 is sort of the cop-out. They take on cellular properties like reproduction. So these are the 4 big stages. I'm going to go into a whole lot more detail. Lots and lots and lots more detail about each of these steps. But broadly speaking, these are the 4 big steps. If you take nothing else away, you need monomers. From monomers, you can build polymers. From polymers, you can encase them in a membrane. And then after you can encase them in the membrane, those polymers encased in the membrane take on cellular properties like reproduction. So, everybody good? Step 1. We got to get the monomers. Organic molecules had to exist before life. We've had these organic precursors, monomers. It is thought that nucleotides and amino acids occurred spontaneously due to the conditions on the early Earth. That is, literally, poof, they just appeared. The question is how? How do we get these complex forms coming about without organisms building them? In Bio 101, you learned all about organic chemistry and how organic organisms create these complex molecules, but we don't have those organisms to build them. So how did? Because we know that before there was life, there was only molecules. Just molecules floating in an ocean. Now, the idea behind this is we had some source for these monomers, for these pre-organic molecules. Somehow they were being built up in great quantities. Now, if they were being built, they could not be destroyed. At this point, remember, early Earth's life, we talked about this a little in the last lecture, there's no oxygen around. Oxygen didn't exist at this point. So there's no oxygen to oxidize them or to break them down. Without oxidizing these molecules, you're really just having them build up and build up and build up. It's almost as if you never take out the trash. Or it's like in the show Hoarders, where they just sort of like keep adding things to their house. There's nothing that breaks it down to move it out. So once we establish that they are being built, they will continue to be built up because there's nothing out there destroying them. Eventually, so many of these molecules built up in the water that they saturated it. The water was filled with these pre-organic molecules, these monomers. They weren't coming together well, but they were just filling up the water. And we call that, I kid you not, the prebiotic soup. Because, you know, it's water-based. So, if we get molecules being built, they won't be broken down because there's not really much oxygen out there to do the oxidizing, and you get this prebiotic soup forming that's filled with pre-organic molecules. So how did we get these molecules to form? And there are three competing theories. There's the reducing atmosphere, the extraterrestrial hypothesis, and deep sea vents. When in doubt, I find that in 102, the answer, it came from outer space, seems to be kind of universal. So let's go through each of these. First off, reducing atmosphere. By reducing, I mean it's the opposite of oxidation. Reducing means you donate electrons. The geologic record shows that the early Earth's atmosphere was made up primarily of water vapor, hydrogen, methane, and ammonia. So lots of water, lots of hydrogen, lots of methane, lots of ammonia. It was a green sky. Those components were really this guy Stanley Miller in the 1950s, he was doing an experiment, and what he wanted to see was if I put all of those chemicals from the early Earth atmosphere into a flask, and then I fire electricity through that flask, what will happen? So he enclosed this, the gases from the early Earth's atmosphere into this ball, and he fired electricity through it. Now, why electricity? What does that represent? Lightning. The early Earth's atmosphere has a lot of lightning strikes. Heck, our current atmosphere has lightning strikes all the time. That lightning is adding a lot of energy to a system. Well more than enough to exceed the activation energy necessary to bind molecules together. So the electrodes replicated the lightning of an early Earth storm. He would have lightning flash after lightning flash. I think it was like 1 a second for like 2 weeks, which of course that was a very short time frame to replicate what was happening over a geologic span of millions of years. So lightning sparks happening, gases you ended up forming. They formed a condensate. They formed water along the edge of the flask. The water dripped down through a condenser as it was cooled. As the water settled at the bottom, it was sampled in order to see what molecules were in there. Then the water was heated back up and sent back up into the atmosphere. It replicated the water cycle that would happen on the early Earth's atmosphere, the early Earth. So you're getting a cool down. It's being concentrated down here. Water's going back up. Lightning strike, lightning strike, lightning strike. He did this for a week. Within 1 week, 10 to 15% of the total carbon in that system was then incorporated into organic molecules. We got an organic molecule from an inorganic source, lightning. So this is plausible using these chemicals, these gases, methane, ammonia, and such. So far, so good. Does that make sense? So this is one way that you could have gotten early Earth pre-organic molecules. Specifically, he noted the presence of hydrogen cyanide and formaldehyde. Now, both of those sound kind of scary. You know, you think cyanide kills you, formaldehyde kills you. But they are actually necessary for building amino acids. And that worked out super well, but then there became an issue. And the issue was we got more information. We figured out, turns out the earlier gases weren't methane and ammonia. They were carbon monoxide, carbon dioxide, nitrogen, and water. We got better data. And we got that because that's primarily what's being vented from volcanic gases. And we know that there was a lot of volcanism in earlier history. So, scientists out there, what do? Right, you run a new experiment now. This time, you incorporate these new gases in. Though what they find, even by altering the initial chemicals, organic precursor molecules still formed in the same way. You ran the same experiment with different molecules, different gases, and boom, you still get organic precursors. You guys don't seem nearly as interested in this as I am. Literally, I'm telling you, life is coming from non-life. I mean, this is a big deal. That's one way it could have happened. It's plausible. Don't know for sure. Nobody was around back then. Another way it could have happened is it came from outer space. Literally, amino acids and nucleotides could have come in on meteors, meteorites, asteroids coming in. They become meteorites as they strike the atmosphere. They burn up. Remember, part of the issue is we need to get energy to get these reactions to happen. One way of getting energy is, of course, through lightning. But what we found too is that these they're called carbonaceous chondrites, so meteors. When they're made of carbon, there's substantial organic carbon residue on them. So as they come through the atmosphere and land, when they've hit, you find organic precursors on that meteor. We talked what happened a lot during the early Earth's history. Boom, meteor strike after meteor strike after meteor strike. It's possible that you could have gotten some organic molecules from this. Because as a meteorite enters the atmosphere, just like lightning provides a lot of energy, what happens when a meteor hits the atmosphere? What do you see from the ground? Yeah, it's like a shooting. I was out walking the other night, I kid you not, and I saw this stupidly bright green meteor flash across the sky. That's a lot of energy. I also started questioning it. Is it an alien, thing going on? No, it was a meteor flashing through that likely had a bunch of copper in it that was just burning up as it went through the atmosphere. That energy can be passed to the gases around the meteor, leading to organic precursor molecules forming. You overcome that energy of activation. So that's another way. It's possible. Third possibility. We've got all these things happening up in the sky. Let's talk about what's happening deep, 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 deep at the bottom of the sea. You could have gotten these key organic molecules developing at deep sea vents. This is called a black smoker. The bottom of the ocean, it's where magma's meeting the high pressure, very cold water, 4 degrees Celsius water at the bottom of the sea. It's called geothermal venting. Broadly, if you look at this image, you can see magma is about 1200 degrees Celsius. You have this reaction zone, 400 degrees Celsius, where cold seawater is beginning to interact with the magma. As it gets closer to the surface, that cold seawater has actually taken in, as ions, many different types of atoms, many different types of ions that are dissolved in the water. And they come out very, very hot. Quickly, once they hit very cold water, lots of very cold water, they cool down. So that leads to a lot of ions, metal ions especially, at the bottom of the sea, right by these black smokers. Provides a lot of energy too. Got hot, a lot of kinetic energy down there. What we find is that temperatures greater than 300 degrees, which we know is happening right where the magma's meeting seawater, and at extremely high pressure. Bottom of the ocean has the pressure is so high that you will be instantly crushed by the weight of it. It could be conducive to forming organic molecules. Right around these vents. Today, we still see an enormous variety of organisms thriving just based on the energy provided by those vents. Hydrogen sulfide and iron at these temperatures creates pyrite and H2, both of which are necessary for creating nucleotides. So at the bottom of the sea, we have the super high pressure, super high temperature metal ions interacting to begin to form organic precursors. N2, which is very abundant on the Earth, could then be reduced using those hydrogen sulfide to form NH3. Do you guys know what NH3 is? It's ammonia. And what is ammonia a super important part of? Say it again? Cat urine. Thanks. Okay, yeah, it is an important part of cat urine, but As far as what we need it for, ammonia is what actually gives it the title amino acid. And what are amino acids used for? Proteins. And what are proteins used for? Everything. So now we're building amino acids, we're building nucleotides at the geothermal vents. So we got these three different hypotheses. The reducing atmosphere that's been shown to produce monomers, the extraterrestrial hypothesis, which could produce monomers, and the deep sea vent hypothesis, which, go figure, can make monomers. All three are tested and shown to work. Does that mean we know which one it is? No. Could be a combination of all three. So we've got 4 distinct stages. Step 1, produce monomers. That's what we just talked about. That could have happened through geothermal venting. It could have happened through meteors hitting the atmosphere. It could have happened through the reducing atmosphere. Then we have the polymerization of those monomers. Step 2, polymerize them. Build big chains of nucleotides or of amino acids. Step 3, enclose them in some sort of membrane. And then step 4, they begin to take on cellular characteristics like reproduction.